Good morning, good afternoon, good evening, wherever you are. Let's just wait a few more minutes. We had a headliner by Professor Susan Handy, and I think we ran a little late there, and so we're transitioning those who attended that session to ours. So maybe we wait another couple of minutes. So Jan, for you, I guess it's still morning. And for Zia and Agnieszka, it's afternoon.
Yes.
Good afternoon.
So Alberto, are we going to have 25 minutes total, right? 20 minutes plus 5 Q&A, or how is it going to be organized?
Right. So one of our speakers, Dr. Akshay Ashok, he will not be joining us, which gives us 4 speakers. We should be finishing at 2 p.m. Sorry, let me get the time zone right. At 1 p.m. Let's stick to the official time zone,
Yes.
Central Daylight Time. Right. And that gives us, I would say, 25 minutes for each talk, and then followed by 5 minutes of Q&A. And so we have, maybe I'll start presenting the session. So I'm very excited to be here. I'm maybe a sort of a budding producer of knowledge in this field. So I'm very excited to be here as a consumer. So this is session 4. Okay, I think Hania is piloting the right session 4. So we're going to start with Dr. Zia Wadud. Apologies if I get the pronunciation wrong. He's going to tell us about some. So Hania, if you want to just keep that slide, which shows the talks. So Zia will present some work that is published and in process, a project looking at the outsized effect that long-distance travel has in the climate damage of passenger travel. So it's sort of a very, we thought he would go first as it's an overview and a good segue to another very exciting talk by Dr. Skowron from Manchester Metro University. So Zia, by the way, is from Leeds. The climate damage from aviation that is most talked about in the press and the airlines is obviously the carbon, the CO2 emissions. But there is a potentially larger component, which is the non-CO2 impact. And so, very excited to have Dr. Skowron be here, and I'm a great producer in this field. I think it's obviously very contentious, points to how some policies that might address carbon don't address other impacts. Dr. Ashok, unfortunately, will not be here. Last I heard, he would also, I think, take Dr. Skowron's talk and make it bring us to the policy world, which is what he's working on at Boom Supersonic. He was at MIT previously. And then we're going to circle into economics. So we have Dr. Brueckner from UC Irvine talking about incentives, to supply side incentives, maybe, if you will, to retire the older aircraft in the industry. And then we'll end up with a project by Kara and I and others thinking about some incentives on the demand side. So before I turn it over to Dr. Wadud, Kara, why don't you step in? And I saw you just sent something in the chat. Haven't had a moment to look at it, but why don't you just step in and also give us your presentation? Great to have you here.
Oh, man. I don't have a presentation to give.
sounds like I'm a little bit back and forth here. So I don't know if I got signed in twice by accident. Anyhow,
There is an echo.
Yeah, I might be going through somebody else's. So I think we need to mute Zia and maybe you, Alberto, or something before I can
Sounds
talk.
good. Okay.
Yeah. Well, it's still feeding back. But anyhow, I have nothing to present. Alberto's the lead author on that paper, and I'm just here to listen. So thank you.
Very good. So, Dr. Wadud, why don't you take it from here? And thanks all for joining us, those in attendance besides those presenting.
Okay, can you hear me, Alberto? And can you see my slides as well, I assume? Yeah, okay. So good afternoon from my side, I guess, everyone. And thanks, Cara and Alberto, for inviting me to give this presentation. So as Alberto has mentioned, this is a work that we have published just last month in Nature Energy, and this was co-authored by my colleagues, Dr. Muhammad Adil, who is at the University of West of England, and Professor Gillian Annabelle, who is a colleague of mine at the University of Leeds as well. So both Gillian and I are from the Institute for Transport Studies at the University of Leeds. So the topic is casting a long shadow, the role of long distance travel in carbon emissions. And to start with a little bit of context, domestic travel emissions. So we all know about greenhouse gas emissions and climate change, and we know that they need to be reduced. And a lot of the efforts are currently focused, especially in the transport domain, focused primarily on the domestic travel emissions. And in order to understand domestic travel emissions in general, we are often dependent on what I call the national travel surveys. In the UK, it's National Travel Survey. In the US, it's NHTS, right? National Household Travel Survey, I believe. So they often cover only domestic travel emissions and ignore the international emissions, or even if they have international emissions, they include only not a detailed picture of international emissions often. So international emissions often get ignored if you want to focus only if you use data from national travel surveys. And also the national emissions inventory in most countries, they consider only transport emissions that happens within the land border of the country and often calculated by fuel sales and things like that. So they often will not consider a resident's travel, say a Brit's travel abroad for holidays or an American's travel abroad for holidays. So the national inventories often miss that part, but you could attribute to that emissions to the citizens of that specific country, right? So that is also something we need to keep in mind a bit. And also then, if you think about the mitigation measures, especially in the transport domain, often they focus on local mitigation factors, especially the behavioral ones. For example, they look very much on city scale, modal share, changing from car travel to buses or rail or to active travel modes and the likes. And the long distance travel, so intercity travel, often gets missed in this type of discussions. So what we were interested in was understanding the role of long distance travel in general. And we got a project from UK Research and Innovation. It's called CREDS, Center for Research into Energy Demand Solutions. So the center looked into demand and behavior related measures to reduce emissions, not just for transport, but for other end use sectors as well. But University of Leeds, we focused on the mobility and transport side, and in that side, we focused on long distance travel quite a bit. So the key research question was actually just to understand long distance travel a bit better, because there isn't enough information on long distance travel. Within that, we were interested in how much do English residents travel, how much of it is long distance, what modes govern the long distance travel, why do people travel a long distance, or what are the purposes, how much of greenhouse gas emissions we are talking about. And also we wanted to look into whether long distance travel or travel in general has peaked or not. Many of you will have already heard about the peak car phenomena that was discussed around 15 to 17 years ago. So we wanted to see that as well. So that was kind of the overall research questions for our project and our paper. We started with, at the very beginning, we had a bit of a trouble in terms of defining long distance travel. There are several definitions of long distance travel based on spatial distance, duration of trip. Sometimes if you spend whether you are spending overnight at another location or not. And often long distance travel is characterized by, for example, it will be low frequency. It will be irregular travel. It shouldn't be a commute type long distance travel and the likes. For our purpose of this project, we used 50 miles as a cutoff point. 50 miles, one-way distance is chosen as a cutoff point for long distance. There's no deeper philosophy. It's just that we have found that if quite a few studies have used 50 miles, and that's why we have used 50 miles in this study. So the main challenge and first thing that we had to do is we had to look at the data sources. As I've mentioned, NTS, the National Travel Survey of the UK, covers domestic travel. That's the typical household survey, household diary survey. But for international, we had to look elsewhere. And the ones we are looking at was IPS, which is called the International Passenger Survey. Now, International Passenger Survey is an intercept survey, not a household survey and diary survey like in NTS, and which means it's not possible to connect one-to-one, one member at NTS to one member at IPS. That's not possible. So when we merge the two data sets, the things that we can do are only on the basis of group averages. Okay, not on a personal basis or a household basis, but as a group basis, and using group averages from NTS and using group averages from IPS and combining them. I wouldn't get into detail into the data fusion thing. The paper has it in detail. If you're interested, please have a look. So in terms of results, the first thing we wanted to touch on is this thing. This is the domestic travel. That's the NTS derived results. What this picture, we find that around 6,400 miles per capita travel, an English resident, and it's around 783 trips per capita per year. This picture shows here the green bit. So this is the mile-wise distribution of the trips. This is the trip mileage band-wise distribution of the trips, of the share of trips and share of miles. So what it shows is, for example, trips between 2 to 4 miles long. So roughly around 27% of domestic trips are 2 to 4 miles long. But that, because these are relatively shorter trips, that covers roughly around, say, 8% of the miles. That's the orange bit. And roughly around 8% of the emissions as well, which is the black dots. So that's if we consider NTS data from domestic travel. 50 miles, if you remember, 50 miles is our cutoff point. If you look at only the right-hand side, the long distance travel, excuse me, only around 2% of the trips, that's the small green bit, are long distance, but that covers around 29% of the miles. and similar share of emissions within the domestic trips. Now, obviously, we're interested in international as well. Looking at IPS data, we find the trips from Great Britain, and this includes both flights, the Channel Tunnel. You know, UK has a underground tunnel with France, and including the sea trips, the ferry trips to Netherlands and France and the likes. We find that only on average per capita, a person takes only 3.1 international trips, compared that to 783 local trips. But that covers 5,400 miles a year on a per capita basis. So that's really large. And air travel obviously dominates within this international travel. 96% of this international travel is done by air travel. So once we combine these two, we find that around a British adult, an English adult takes roughly around 11,900 miles, travels 11,900 miles per capita. And this is the combined travel between including domestic and international. As you will see, still the number of trips, they are dominated by smaller trips, small distance trips. But if we look at the longer distance trips, these are the small bits, including both domestic and international travel. This becomes only 2.7% of the trips, but that covers around 61% of the miles. That's the orange bit. And that is responsible for around 69% of the greenhouse gas emissions, which is the CO2 equivalent emissions. I wouldn't get into the detail of why air emissions are higher. I think the next presenter will touch on that, but just to let you know that we have used a multiplier of 1.9. So any emission that's coming from flights, we have multiplied that 1.9 to consider the non-CO2 and other radiative forcing, and because the emissions are taking place higher up in the environment. So the number that if you want to take away one message from this presentation, that is this number that we are trying to polarize, which is 360/70. It's less than 3% trips, roughly around 60% of miles, roughly around 70% of emissions coming from trips more than 50 miles one way. This includes both aviation and car and rail. Looking into mode of journey a bit more in detail. So the orange bits here, orange and brown bits here are shorter distance trips. The blue bits here are longer distance trips above 50 miles. So naturally, shorter distance trips are much higher. If you remember, car dominates. In the shorter distance, there's quite a bit of rail and bus. In the long distance trips also, there's quite a bit of car. You probably cannot even see air and rail. There are such few share of trips. But if we go to miles per capita basis, then you see that air travel and car travel becomes more dominant and almost equal in terms of mileage on a per capita basis. And if you go to emissions, because air travel emissions are weighted higher, you see that air travel starts dominating and long distance travel starts dominating in a person's or in an average person's travel emission profile. Okay, so that's the modal analysis. And what we also did is, so all of these are slightly dated in a sense. The project started actually in 2019. So the latest data we had was 2017. But we also, so this is 2017, but we also looked into 5 years interval for the last 20 years before 2017 to try to see if we can find any trends in these travel patterns. So what we see in general is that domestic travel is falling within England, both long distance and short distance. but international travel is going up, and that is being dominated mainly by air travel. We also find rail travel is rising. This is this violet bit, both for domestic short and long distance. Car travel is falling, especially for domestic travel, both long distance and short distance. And that kind of brought us to the same conclusion as was seen roughly around 15 years ago, that in the Western economies, peak car may have happened. The people's travel have reached a plateau on a per capita basis by car, and it has started falling. However, peak travel may not have happened. Car travel may have been falling, but because air travel is going up, total mileage is still going up. That's what we found. Who knows what we find in 2022 after the COVID, but the generic conclusion we have is that yes, peak car has happened, but we haven't reached peak travel yet. And then there's a question of peak emissions. Although we can say confidently that we haven't reached peak travel yet, it was still going up. Peak emissions seems to have, emissions per capita from transport seems to have stabilized. And the reason is, although air travel is going up, flying has become more efficient, right? So that's why the peak emissions is still in a plateau, and we cannot confidently say it will go up again or it has started going down. It has been kind of stabilized a bit for the past few years. So that's the modal one. Looking at the purpose of journey, for shorter distance, it's the other purposes. It's not commuting or leisure or social. It's other purposes like shopping and escort trips, which dominates the number of trips. But in terms of mileage, it's leisure and social travel which dominates. And this is really interesting because a lot of focus on decarbonization is often on commuting trips, like encouraging people to car share, encouraging people to take buses or trains for their instead of car travel. However, it does look like that it's this leisure and social which dominates the miles per capita. And if you consider the emissions, then again, because air travel is so much more polluting, and a lot of air travel is because leisure and social dominates carbon dioxide equivalent emissions on a per capita basis as well. And naturally, long distance travel dominates the mileage as well as emissions in general. In terms of trend, again, the key point here is that business travel is actually falling, both in domestic short distance and domestic long distance trips. Even in international long distance trip, it seems like business travel has been falling since 2007. But the key one is that traveling internationally for social purposes and leisure, they are the big growers. It's a social one which is growing even more than leisure and holiday trips. So that's from the trend analysis. So why does it all matter is the next point. So what we have done here is we have done a few what we call thought exercise. These are not running sophisticated transport models and the likes. This is taking our relatively aggregated data and trying to run a few what if scenarios. We are not looking into the policies, how this can be done, but just looking at what happens if this happens. So we have tried several such thought exercises. There are a few more in the paper itself. So the one I wanted to highlight on is the first one we looked at is, okay, what if we move all of the trips less than 8 miles that are currently taken by car to bicycle and walking, okay? How we are going to do that, we didn't look at it. It's just looking at what happens then. So what we find is that if we do that, we can reduce CO2 equivalent emissions by around 9%, 9.1%. But we have to shift 55% of the trips, okay, on an average basis, on a per capita basis. That's a huge number of trips. Looking at now longer distance trips, so which is all car trips greater than 50 miles, looking at them, and what happens if we move them to trains. Reduction is slightly lower than the previous one, 5.2%, still same order of magnitude, but only 1.8% of the trips are affected because long distance trips are much fewer. So the gains are quite high in that sense. Next one we looked at is, okay, what happens if we can move all the flights less than 1,000 miles, so all the trips, flying trips, less than 1,000 miles to train. Europe and England, England doesn't have as much good high-speed rail, but Europe does, and a lot of the holidays take place there. So less than a 1,000 mile is feasible-ish. That reduces emissions by 5.7%, but only 0.17% of a person's trip, average annual trip, is affected because of that. And if you start taking holidays within UK, these are obviously extreme scenarios. Instead of going abroad, you can make a huge saving of 28% emissions. That affects only 0.2% of the trips. And this brought us to kind of deriving a new metric.
Zia,
yes.
Sorry to interrupt. We started late, but just to know that we're 30 minutes into the session. Okay, thanks.
Oh, okay. This is my second last slide, I think. Yeah. Okay. So if we look at, so we have this thing called we have developed this thing called emission reduction sensitivity, trying to understand which measures are more effective in terms of reducing emissions more, but affecting as few trips as possible. And these are the kind of the numbers that we get. So if we look at shorter distance trip, reduction sensitivity is only 0.16, which means if we follow this type of a strategy, we need to reduce a lot, we need to move a lot of trips, which means the reduction sensitivity is very low. If we focus on longer distance trips, the reduction sensitivities are an order of magnitude or 2 orders of magnitude or sometimes 3 orders of magnitude higher. So the lesson is that focus on longer distance trips to have the biggest gains. So concluding, LDT has a very large role in miles and emissions, 360-70, keep that in mind. We want to focus also on the emissions accounting framework. I think we need to move forward from just a nation geography-based accounting framework to an emission attributable to a person. So travel-based accounting framework. I know UK will do that from 2020 to 2033, but maybe other countries should get into this framework as well. Including international travel in travel surveys so that we understand international travel better. Local initiatives are good, but LDT, the long distance travel, offers the larger potential for cut. So if we have a fixed resources, that's probably where we should focus more, because that also leads to less disruption in travel, and think about probably more draconian rules, even thinking about a travel carbon budget, frequent flyer levy and the likes to have the most amount of gains in terms of reducing carbon emissions. And that's pretty much it from me. As I said, the paper was published in Nature Energy. Please have a look there if you're interested. Thank you.
Thank you, Dr. Wadud. That is a great way to start the session. In the interest of time, let me just go straight to a question that Kara posed in the chat box, and then maybe we'll see if there's any other question from the audience. So I'll just read it out. I was reading online that CO2 equivalent per seat mile by air is about half of that of an efficient car, such as a Prius. And so Kara is asking about, I'm surprised your blue pie piece grew so much for air emissions per capita. So if you had any thoughts on that, maybe, most cars are not Priuses.
I think what Kara is mentioning is about emissions, not on a per capita basis, but per vehicle miles or per passenger miles and the likes, which is very different from what we are doing here. We are looking at a person's travel profile. And it's true, if that estimate is correct, then my blue should be less, right? My blue should be slightly less compared to my, let's go back to the slide. Yeah, so if that is true, then my air should have been a bit less here and car should have been a bit higher on a per capita basis, but a lot depends, I think, on where it is happening. This the load factor is a very important factor in terms of whether you are calculating the emissions per passenger mile in a fully loaded aircraft versus how also the load factor in a car, how many people are in a car. We have included, for example, long distance car travels will often have higher occupancy compared to commute car travel. So your per capita emissions, per passenger mile emissions in long distance travel in the same car will be less compared to a one-person commute travel. So all of those are kind of included in our model. And also it is important to keep in mind whether that one is the one example you gave, is that only carbon emission or that includes the radiative forcing of flight. So that is also important to consider. Does that answer somewhat?
Yes, I think it does, unless Kara wants to chip in. That's good. There are lots of different avenues by which
Yes.
the metrics might differ. It's very good. So in the interest of time, let me ask whether there's one question from the audience. Very briefly, question, very brief answer before we turn over to Dr. Skowron.
Can I ask about the car gains? If you're switching to walking or bicycles, but if you're switching to an electric car, then you get the same thing, 9.1%, right?
Assuming your upstream electricity is coming from fully green electricity.
Okay, so you're counting all of that kind of stuff then, the upstream part, right?
We didn't look into electric vehicles per se, but if you make this an electric vehicle and green electricity is zero carbon, for example, then we will have kind of the same number.
Okay.
But it's a bit tricky because if it's an electric vehicle, your 50 miles will also be included there, right? If you are traveling on an electric vehicle, you are not switching only less than 8-mile trips to electric vehicle trips. You are switching all car trips to electric trips.
Right, okay.
So these numbers will, I suspect they will have to be added, I suspect, in that case.
Right.
But the key point here, sorry, just a point is that, again, for electric vehicles, I think in the UK, you have to change 32 million vehicles to electric vehicles. That's still a huge number that needs to be switched to electric vehicles. And in the US, it will be even more, right?
Right. So thank you very much, Dr. Wadud. Let me turn over to Dr. Skowron. Take it away, Dr. Skowron, and thank you for joining.
Hello to everyone. Can you hear me well?
Yes.
Yes, okay. So you want me to share the screen? Yeah. Wait. Okay. How that is? No. Okay. Okay. So hello to everyone. I'm going to introduce the general perspective of the climate impact on aviation, concentrating on non-CO2 mainly. However, not only, because yeah, not only. So I will, yes, introduce it shortly, then I will show how different non-CO2 is from CO2, and then I will also try to show how tricky can be mitigating non-CO2 climate effects. So yes, briefly, that's the outline of my presentation. Okay, so it works that way. Okay. So here, as an introduction, I wanted to show you how that aviation contributes to warming. So on one side, you can see the warming footprint of aviation. On the other side, you can see the carbon footprint of aviation. And I think it nicely visualized that the aviation contribution to warming is beyond carbon only. And it can be observed that regardless the scenario, the warming footprint of aviation is at least twice as large as its carbon footprint in the coming decade, clearly highlighting that the non-CO2 effects are non-negligible to assess the contribution of aviation to global warming. Aviation contributes to the global climate warming. Aircraft emissions affect atmospheric composition and modify the cloudiness, which in turn influence the radiative balance of the atmosphere. The present contribution of aviation to global CO2 emissions is around 2.4%. Global aviation fuel use and CO2 emissions have increased in the last 4 decades and are anticipated to grow. The growth in air traffic results in an increase in the CO2 contribution to the warming. In addition to CO2, other species emitted by aviation also impact the global climate. And those other emitted species are called the non-CO2 emissions. So collectively, aviation CO2 and non-CO2 emissions are calculated to represent about 3.5% of the present day total anthropogenic radiative impact on climate. But further increase in air traffic as projected will increase this absolute and relative contribution of aviation to global climate change. So 1/3 of aviation impact on climate comes from CO2, the greenhouse gas. Due to its fractional millennial lifetime, aviation CO2 accumulates in the atmosphere, providing the majority of the long-term warming. However, there are also other concerns over aviation's current and future effects on climate, and that they are related to its non-CO2 emissions. The non-CO2 emissions that can affect climate include oxides of nitrogen, soot, which are the small particles of unburned carbon, water vapor, and sulfur dioxide. These emissions affect atmospheric composition and changes in cloudiness, which changes the radiative balance of the atmosphere. So the direct radiative forcing of water vapor emissions is currently assessed to be small and positive, but they are highly dependent on the altitude of the emissions. So its importance increases when emitted higher into stratosphere. Emissions of sulfate result in a negative direct radiative forcings. Emissions of soot particles results in a direct positive radiative forcing. In addition, sulfate and soot emissions can also interact with low and high level clouds, respectively. However, these climate impacts remain highly uncertain, both in terms of design and magnitude. So you can see it all very complex. Every part of this non-CO2 bit behaves slightly different, and sometimes producing more effect, sometimes it's less. So it's not a straightforward discussion about non-CO2. It's quite complex, and yes, we have to take into account all these different behaviors and responses. The largest non-CO2 effects from aviation on climate are currently understood to be the formation of contrary cirrus and effects on atmospheric chemistry from emissions of NOx. So condensation of water, so how the contrails, for example, appear, how it happens that we can observe that. So the condensation of water vapor on co-emitted soot particles in cold ice supersaturated regions of the atmosphere results in the formation of condensation trails that are contrails. Contrails can persist, spread, grow into a contrail cirrus cloud coverage. The net radiative warming effect of contrails and contrail cirrus is the residual of warming, mostly at night, and cooling effects mostly by day. And emissions of NOx from aircraft engines results in the formation of tropospheric ozone, which is a greenhouse gas, but also results in the destruction of ambient methane and other greenhouse gas emitted from other sources, with a net positive forcing from the balance of these two, ozone production and methane destruction, but also it's associated to other cooling effects like reduction in stratospheric water vapor. So again, this is kind of very complex. It's not a straightforward response. It happens on different time scales, different space scale. In addition, NOx also can be involved in direct in some aerosol interactions, which again will cause a slightly cooling effect. Altogether, for net NOx, the warming effect dominates based on the current understanding. Interestingly, some recent studies suggest that depending on the future background scenario for surface emissions of ozone precursors, the sign of the net NOx radiative forcing could vary from positive to negative, and it remains highly uncertain. So actually, we can reduce the net NOx effect of aviation only by mitigating the anthropogenic emissions in general from the surface. So both CO2 and non-CO2 are very different in their nature. If quantified on a radiative forcing basis, the CO2 and non-CO2 related impacts account for about 1/3 and 2/3 of aviation total climate impact, respectively. However, this relative contribution of aviation's CO2 and non-CO2 impact might change in the future, as the non-CO2 impacts are dependent on the background atmosphere and dependent on the rate of growth of aviation. I will be showing it later on. The non-CO2 impacts of aviation have a greater uncertainty associated with them compared to that from CO2. Additionally, non-CO2 and CO2 emissions have very different atmospheric lifetimes, and therefore the resulting radiative forcing from these species differs substantially in timescales. CO2 remains in the atmosphere for millennia, whereas non-CO2 related radiative effects are short-lived, persisting for hours, months, and years in case of methane. Consequently, long-lived gases such as CO2 are considered well mixed. The climate impacts of CO2 is effectively independent of emission location, while the radiative forcing from non-CO2 components are highly dependent on location and time of emissions. These are the most important differences between these two components, and I think it's worth to know and understand that they exist. Yes, they are. Now I wanted to kind of let you imagine, because yes, they are very different. Also, the way how they respond to emission on different timescales and various emission scenarios. So I thought I drew some hypothetical scenarios and let you imagine how to help you to imagine how different behaviors their different behaviors. So in each of the few next slides, you will see this few drawn scenarios, and where CO2 is blue, non-CO2 is pink, and the net, which is the CO2 and non-CO2, is green. So let's start with the business as usual scenario. We can see that the net non-CO2 effects of aviation currently represents 2/3 of the total radiative forcing of global aviation. This fraction is not fixed, but it is dependent on the growth rate of aviation. So if global aviation activity levels continue to increase, these non-CO2 effects will continue to dominate the total radiative forcing as it happens now. let's take into account the zero emission scenario. So we stop emitting the aviation emissions at some point. So we will see that the no CO2 is emitted, but it also does not go out because of its lifetime. It will be there forever, kind of. Non-CO2 will reduce due to the time scale effect. So once there's no emission, the non-CO2 effects will disappear at some point. So if we stop flying now, we would reverse some of that warming, not everything, some of that warming. So let's take into account now the constant emissions. So yes, at some point we will keep the emissions as they are now, for example, and they won't increase. So we will see that CO2 will still increase, and non-CO2 kind of follows the emission path. And non-CO2 forcing would equilibrate at some point, whereas CO2 emissions will continue to accumulate in the atmosphere, and because of its lifetime. So therefore, the warming will continue to increase, even if we keep emissions as they are now. So now the scenario that will take into account the reduction of emission. For example, people will decide to fly less, or we use the SAF fuels or better engine efficiency. The various backgrounds for that reduction of emission. So there is a chance that at some point, if we can get the net aviation impact might get constant. The CO2 will still increase, but the slope of this increase will depends on how strong is the decrease, and the non-CO2 effects will follow the emission path. So that's here we can kind of pose an interesting question. Introduce the question: how much do we need to reduce flying to achieve no further warming? Is it possible? So we at some point we exercised these hypothetical scenarios, and we introduced some real numbers behind this imaginative scenarios. So what we found out that this figure illustrates the warming impact of aviation resulting from different growth scenarios, accounting for both CO2 and non-CO2 forcing. So in general, aviation is projected to cause a total of about 0.1 degree of warming by 2050. The reduction due to COVID to date is small and is projected to only delay aviation's contribution to warming. Interestingly, zero growth scenario will still cause rising temperatures because the CO2 that keeps adding up. So what will halt further warming is the reduction of air traffic by 2% each year. And what is interesting to observe here is that if aviation CO2 emissions decline, the non-CO2 warming reduces dramatically. The underlying message from this could be summarized as: if CO2 emissions are reduced, the non-CO2 impacts are reduced or kind of look after themselves. This is a nuance that is not widely appreciated. And at the moment, the non-CO2 aviation impacts dominate 2/3 over 1/3 of CO2. However, the reasons for this is the underlying growth rate of aviation. So if emissions level off or decline, a different ratio results. And that you can see it on that. There is this fraction of non-CO2 to the total changes with different CO2 emissions. So this is where you can see how the ratio will be different with different growth scenarios for aviation. So yes, that's I think that introduced how different CO2 and non-CO2 in terms of their behavior and responses are. The same can be when we try to mitigate the aviation environmental effects. It's not a straightforward task. But in general, there are several research groups and research publications that have focused on solutions to mitigate the climate and air quality impacts of aviation. This can be broadly classified in 3 approaches to mitigating the environmental impacts of aviation. The first approach involves the use of low greenhouse gas fuels, such as sustainable aviation fuels, to address CO2 emissions. The second, sorry, where I, okay. Okay. The second approach focuses on operational strategies to mitigate contrail impacts. The third approach utilizes technological innovations to reduce NOx and air quality impacts. The reduction of fossil-based CO2 emissions is the main policy requirement associated with climate protection. If the drive for CO2 reduction includes uptake of SAF, for example, then water vapor, sulfur dioxide, and soot emissions will be potentially reduced as a co-benefit. If liquid hydrogen is considered, then a larger direct water vapor emission is expected. And together with the reduced soot emissions, it's likely that the contrails formed with will have different characteristics in terms of density, lifetime, and radiative effects. Emissions of NOx are thought not to be impacted by SAF, since they are a function of combustion, not the fuel source. Alternate fuels, however, may enable new combustor designs that could in turn reduce NOx emissions. There are certain technology solutions that, by increasing the component efficiencies of a gas turbine, can reduce both CO2 and NOx emissions. That can result in a reduction in both climate and air quality impacts. The other option is the navigational avoidance of cold, ice, supersaturated regions. And has been suggested as a means of reducing the occurrence of persistent contrails. This is currently very low. There is currently very low confidence in this mitigation measure. This is because of the challenges in making accurate predictions of persistent contrails on the time and space scales required for operational implementations, but also a lack of the analysis of reductions in contrail series reinforcing versus potential carbon dioxide reinforcing increases from changing flight levels, routes, etc. So there's plenty of interconnections, and it's not so once you're touching one part, the other are likely to be affected as well. So one of the fundamental problems with non-CO2 mitigation for aviation is that there can be trade-offs between either technologies, operations, or policies that target non-CO2 effects, which results in increased CO2 emissions, for example. This leads to a question of, is it of net benefit, which is very difficult to answer because since it invokes a metric-based comparison of non-CO2 radiative effects with the CO2 radiative effects, and they both act on very different lifetimes. As aircraft technology improves, there are strong encouragements to decrease emissions and other environmental impacts, and these improvements are often used to mitigate air quality and climate impacts. However, trade-offs occur when multiple environmentally harmful emission components respond in opposite directions than engine or aircraft design change. So for instance, if fuel burn were to optimize with no constraints, the NOx emissions would increase significantly due to higher combustor temperatures and pressures. So there are these trade-offs between these competing components. So for example, here between NOx and CO2 when revising an engine and aircraft design. There are some, however, in terms of these trade-offs, there are some recent studies that, for example, if you consider only climate impacts on its own, so these studies have shown that reduction in aviation NOx emissions do not provide clear climate benefit if these reductions are achieved using design changes that increase in CO2 emissions. So it's not always less means better because it depends what happens afterwards, and you have to be careful here. Another example is SOx emissions that in general, they lead to the formation of sulfate aerosols, which can exert a negative radiative forcing by reflecting incoming solar radiation. So in general, it cools the climate, so it is kind of a positive effect. But SOx emissions also contribute to an increase in particulate matter, which has adverse effects on human health. Or there are also trade-offs between non-volatile particulate matter emissions and NOx emissions. There is still very little work on these interdependencies. But in general, some current combustor technologies developed originally to reduce NOx emissions are not always so effective in reducing soot emissions. So so they are the inherent trade-off between the conditions to reduce NOx and soot. So again, you have to be careful to not make things worse. So yes, there is an appetite among some stakeholders for non-CO2 mitigation of aviation effects on climate, but there are also serious reservation over recommending definite courses of action until there is a better quantification of the actual effects and further studies on the trade-offs between non-CO2 reductions versus potential CO2 increases. So one of the main aspects emerging from this talk, I hope, but also seen in various assessments, is the fact that the linkages between aviation non-CO2 and CO2 emissions exist, and that they cannot be considered in isolation, since any mitigation efforts on non-CO2 may have consequences for CO2 emissions, but also similarly between non-CO2 emissions. So, and it is something I find very important and crucial to understand, and something something worth to be aware of. It is realized that this interrelations represent a serious barrier to technology development and policy making, but I believe there's no shortcuts, and the underlying danger is of either ineffective and expensive efforts which are not easily reversed, or making matter worse in terms of the total climate effects of aviation. So again, we have to be careful here. And summarizing is, I would say that considering future changes in atmospheric effects are vital in taking decisions on future technology development pathways, particularly under circumstances when reducing non-CO2 emissions or effects may be at the cost of either extra CO2 emitted or a loss of full opportunity to reduce aircraft CO2 emissions. The reduction of CO2 emissions, I think it should remain, I believe, at the top priority because of its well understood, powerful and persistent effect on climate. And no mitigation should be done at the cost of CO2 because there is a huge potential that it will end up on a different end. It will be causing climate disbenefit simply. So this is something we have to take in mind, that we understand CO2 and it is a powerful greenhouse gas and we can reduce it. Thank you.
Thank you, Dr. Skowron.
Okay. Yes, and also because
go ahead.
Okay. Yeah, I just wanted to, because this is just a small touch of what it really is and introduction to various topics. So if you are interested, there is a paper that explores in details and provide a critical review of what we understand, what we don't, what still we believe has to be done. Thank you.
Thank you. There are some reactions in the chat box, but why don't I first turn to Jan? I think you've unmuted. You have maybe a comment or question? Jan?
Oh,
do you want to?
sorry.
Yeah.
I didn't know you were talking to me. So my question is about contrails. I had always thought that contrails would reduce global warming by reflected sunlight, but evidently there's a countervailing effect. Could you explain how that works? Again?
It depends. I'm not a contrail expert, so I'm not able to go into huge details, but generally it depends on the time of the day. So yes, so yes, the contrails in general, not only, I think it's also the region. I've recently seen a presentation where it was shown that it depends also on the region where it's emitted. It can again cause warming or cooling, but for sure the well-known behavior is that the day contrail in general is cooling, and the night contrails is warming. It's because the night contrail mostly catch the radiation from the earth, and the day contrail scatters the radiation from the sun.
Okay, thank you.
Yeah.
So I have a question, and then maybe we can allow a few more minutes for someone else. I've been reading Dr. Skowron's papers in the past couple of years, and I highly recommend them to everyone. And I get the point that it's uncertain. I think it's a very convenient point for the airlines that like to ignore the non-CO2 impacts, and they even thank you for flying carbon neutral. They're buying an offset at $1 a ton, $5 a ton, and they totally ignore the non-carbon impact. And then people, when they say, "Oh, I'm flying carbon neutral," they take it to mean I'm flying climate neutral, and that's very different. So there's a lot of greenwash. And now, how can we educate the public that aviation can contribute? So if I got the point right, that it can contribute to up to 1 degree of, whether it's Fahrenheit or Celsius, it's still a huge thing. By 2050, right? And it's not about banning aviation, as Dr. Wadud mentioned later. And there's a lot of demand for travel, myself included. But how can we cut the low-value trips, right? Either people directly doing that or induced through pricing and other. Yeah, so education has to be. This is exactly what we're doing in this session today, right? It has to be, top of mind for people, right? That this is a hugely damaging, but highly valuable for people and for society, but also hugely damaging.
Well, I mean, it touches also the ethical issue, because we can we say people to don't fly? It's difficult. I don't think we can do it. And yes, the non-CO2 is kind of totally neglected in various treaties. It's not taken account by policies, and but it's one of the reasons is because it's so it's not straightforward, and it's so complicated to because all the measures we have are based, or metrics are based on CO2, are based on this well understood, well behaved gases, and non-CO2 kind of goes away from all these well-known and predictable patterns. So I'm not sure how to do it. I don't know. But obviously, if we fly, yes, if we fly less, yes, both CO2 and non-CO2 will be reduced significantly. And there are several studies that show that. And actually, in the light of the need to substantially reduce the climate impact of aviation, and actually the current immaturity of clean technologies, because even if we, yeah, okay, that's another topic. It has been suggested by and demonstrated the climate neutral aviation can happen through air traffic reduction, and this is the quickest and the most straightforward way. But I'm not sure. The other part you touched about educating people and how, yes, I don't know. it's and it's more on an ethical basis than scientific basis. Because I'm not in a position to say, okay, you can't fly. Yeah.
Thank you, Dr. Skowron. Is there maybe another question? There's an interesting exchange across the papers in the chat. maybe one more question, or shall we move on to Dr. Brueckner's talk? Maybe we'll just move on then. Dr. Brueckner,
you.
please. Thank you very much. Thank you.
Okay. All right. This paper is about a policy to get rid of old airplanes and thereby reduce the carbon emissions of the aviation industry. And it's co-authored with Matt Kahn and Jerry Nicholsberg. So as we know, aviation accounts for a small share of global carbon emissions, but a bigger share of the emissions from transport. Now, in the United States, the government is helping with development of sustainable aviation fuels through various subsidies and other interventions. But that's really the only government policy in place to reduce carbon emissions from the aviation sector. So what this paper does is it explores a potential program modeled on the United States 2009 Cash-for-clunkers program, which led to scrappage of old cars. So the government paid people to scrap their old cars, in effect, giving them a voucher to use for the purchase of a new car. This program was very successful. It led to the scrappage of 700,000 cars, but it cost $3 billion. And the money ran out in a few months. So our idea is to pay major airlines to scrap rather than sell old retiring aircraft. And what this would do is it would eliminate ongoing emissions from the use of these planes by the purchaser. And who are the purchasers? They're startup carriers or airlines in developing countries. So why is it a good thing to get rid of these old planes? Well, it's because the fuel efficiency of new planes is rising. Here is an inverse measure of fuel efficiency, gallons per seat mile. This is the trend across the 6 largest US airlines over the 1990-2000 period. So that you can see gallons per seat mile is going down. And the reason is that the newer planes that are being used are more fuel efficient. They have lower gallons per seat mile. So there are various other papers in the economics literature. I realize now that this is a tiny slice of a much vaster literature across disciplines. But anyway, there are papers by me and a co-author and some people in Japan looking at the tax effects on fuel usage by airlines. In other words, higher taxes mean lower usage. There's a paper by Fajeda and co-author about airline responses to the EU emissions trading system. Airlines are taxed for their emissions in the EU under this system. And then there are other papers about operational responses to higher fuel prices, one by me and the same co-authors. So anyway, that's a little picture of the economics literature on this topic. So suppose you want to run a Cash-for-clunkers program in the airline industry. What kind of information is needed to do that? Well, first of all, you need to know how much you need to pay an airline to scrap a retiring plane rather than selling it. So in other words, you want to take planes that would otherwise be sold when they're retired, and you want to convert that decision into a scrappage decision. And you've got to pay the airlines to do it, otherwise they wouldn't. They would sell the plane. So the question is, how much money do you need to pay the airlines to scrap the plane? The second piece of information you need is, what are the foregone carbon emissions from scrappage? So the foregone emissions are the emissions that would have been generated by the old plane over its remaining life, minus the emissions of a new plane that would be used in place of the old plane following the scrappage of that plane. And so those are foregone carbon emissions. And what one can then do is one can compute the cost per ton of foregone emissions, right? You know how much you need to pay, and you know the foregone emissions resulting from scrappage. So then you can compute the cost per ton. And you can compare that cost per ton to the social cost of carbon emissions. And if the cost per ton is lower, then this money is well spent. In other words, it's a good thing to spend money convincing airlines to scrap their planes. So let's consider the two pieces of this enterprise in sequence. First, estimating the size of the clunkers payment. So essentially, the clunkers payment needs to equal the difference between the aircraft's market price, that's what the airline got by selling it, and its scrap value. Now, what's the scrap value? Well, that's what you could get by selling the plane to a scrapyard that would tear it apart and sell the materials in the plane. Another element of scrap value is that the airline may want to keep the plane and park it and use it for spare parts. If it has a fleet of planes of the same type that it's gradually retiring, parts are going to be needed for the planes while they continue to operate, and the retiring plane could be used as a source for these parts. So where do we get the market price? We get the market price from aircraft blue books, which give the yearly prices of planes by type and age. So we got access to some of these books, which are expensive to purchase through our connections in the industry. Now, so that's the easy part, getting the market price. The scrap value is not so easy, and we get it by estimating a logit regression using data on the scrap versus sale decisions for retiring aircraft. So in other words, that we're going to have a 0-1 variable, which is scrap or sell. And then we're going to regress that on a bunch of stuff. And we're going to end up getting the information we need out of that regression. I should point out, maybe it wasn't clear, that airlines do scrap their planes. In other words, they don't sell all of the retiring planes. They scrap a bunch of them, a lot of them, in fact, but they still go ahead and sell some of them. Okay, so the explanatory variables in this logit regression are the market price and aircraft characteristics. And we think that the characteristics determine the scrap value. Okay, so slightly more formally, we can say that the airline's scrap value is x plus beta, x times beta plus epsilon, where x is a vector of characteristics, beta is a coefficient vector, and epsilon's an error term. And if we let P denote the market value, then scrappage occurs when the market value, P, is less than the scrap value. And we can estimate beta by a logit regression with a scrappage dummy as a dependent variable and minus P plus X beta on the right-hand side. And the clunkers payment, that's the amount you have to pay to scrap the plane, is the difference. It's P minus X beta hat, where hat is the estimated beta. Now the question is, which planes are you going to pay this amount for? In other words, the airline, what the government would do is it would ask the airlines, tell us which planes you're going to retire next year, but don't tell us what you're going to do with them. And then the government would figure out which planes have a scrap probability less than half. In other words, they're likely to be sold. And then it would pay this amount to the airlines if they chose to scrap those planes instead of sell them. That's the idea. And so how do we know about this scrappage versus retirement outcome? Well, we use data on aircraft histories. And they show retirements over the 2015-2019 period. That's the period for which we have price data. And they do it for the 6 largest US airlines, and they show the scrap sell choices. I'll tell you more about that in a second. Make sense? So we're gonna figure out how much we need to pay through this method. Now, what about estimating foregone emissions? That's the other piece of the story. What we have is annual fuel usage data by aircraft type and airline from US government data. And then we also have carbon emissions per metric ton of fuel. And so we use we have over 5,000 aircraft histories from a public website that we use to estimate the lifespans for each plane. In other words, how long is a plane operated between its manufacture and its scrappage when it stops being used. So then we can compute the remaining life for each retired plane. We know when the retirement decision occurred, and we know how much longer the plane was going to be used then. And so annual foregone emissions from a scrappage decision equal own emissions. That's the plane, the emissions of the plane that's being retired, minus the lower emissions from a new plane of the same size and range. So it's basically the difference between emissions between old and new planes. And so we can compute the discounted value of these emissions over the remaining life of the retired plane, and that's foregone emissions. Sort of get the idea? Okay, here's the data set that we use to estimate our logit model. This is the logit data set for the US. And the planes on the left-hand column are the plane types that are being retired by the US carriers in the 2015-19 period. Here's the number being retired. You can see that 757-200s were the most retired airplane. And then here's the percentage of the planes that were scrapped. The average is around 2/3 for all of these planes. So in other words, there are plenty of planes being scrapped. Here's the retirement year over our period. Here's the market value of the plane. Some of these planes are not worth much. An MD-88 is worth $1.2 million. 747-400 is worth a lot more, 10 million. Here's the plane's capacity. Here's the retirement age. You can see that the planes tend to be retired, around 25 years of age. And here's the number of planes of that type in the airline's fleet, the average value. So what we're going to do is we're going to use all of this stuff in a logit regression. And the logit regression, we run it two ways. We try to include characteristics, like the age of the plane and its capacity. But then we also do a different thing where we just have fixed effects, dummy variables for the type. And that means we have to drop some of the characteristics. That regression works better. The dummy variable regression also has age in it and some other things. Okay, so I'm not going to show you the logit regression. This paper is on my website. You can go look at it if you're interested. Well, here's the logit regression, sorry. So you can see that here's the first regression that doesn't have any dummy variables in it. We have to constrain the market value coefficient to be -1. That's what this approach tells us. So this says that bigger planes, higher capacity, have bigger scrap value. When an airline has lots of planes of that type in its fleet, the scrap value is higher. Essentially, these coefficients are telling you how the scrap value varies. But then the second regression, we delete the capacity since that's determined by the type. But we keep the age and the type count, and then we have a whole bunch of dummy variables for the types, the aircraft types. They're all negative because the one that we exclude is more scrapped than these ones. We can see that the percent of correct predictions is pretty good. It's 87%. In other words, we correctly predict 87% of the scrappage decisions. Okay, now here is the here's the bottom line on this. I wish I could get rid of this screen here. I want to get rid of it. All right. All right, so here is the numbers that come out of this. So let me first say that there were 585 planes retired during the period. And there were 65 of those planes had a scrap probability less than a half. So those are the planes that we want to target with the Cash-for-clunkers program. And so this table gives you the relevant numbers for these 65 planes, and the bottom line being the cost per ton of foregone emissions. So here are the types that were likely to be sold, not scrapped, upon retirement. Here are their market values. Here's the fitted. Well, never mind. Here's the gallons. Annual gallons used by the planes on average across the different types, and that's going to give us emissions. And then we have the remaining life. Not huge amounts of remaining life. The A320-200 has an average 10-year remaining life. So here are the own emissions numbers in tons, annual tons, or discounted tons per year. And that comes from the gallons number over here. And here's the clunkers payment. This is kind of interesting because it tells you how much you have to pay the airline to scrap the plane. And the clunkers payment ranges from a little less than $1 million for a 757-200 up to $7 million for an A320-200. Now, what we want to do is we don't want to just use the own emissions. We want to use the own emissions minus the emissions from the new aircraft. And so we have to multiply own emissions by 1 minus delta, which is the factor that tells you how much more fuel efficient the new replacement aircraft is. So that number varies a lot. So the last two columns here give the cost per ton of foregone emissions. The first column is unadjusted. I'll explain the adjustment in a minute. And so if you take a look at these cost per ton values, they're pretty small. They range between basically $2 per ton of foregone emissions up to 16. But we know that the social cost of carbon is way above these numbers. A benchmark value we use is $51, which is a recent White House number, but other much bigger numbers have been floated by the EPA up to almost $200. So these numbers are really small. They remain small if we do a cost of public funds adjustment. Essentially, what that says is that when the government raises money, it distorts the economy. So $1 of tax revenue really costs more than $1. And the number we use is 1.3. So we inflate these numbers by 1.3 to get the cost per ton of foregone emissions with the cost of public funds adjustment, and they're still way below any reasonable estimate of the social cost of carbon. So the bottom line is that money spent on clunkers payments to convince the airlines to retire these planes, hypothetically, over the 2015 to 2019 period, that money is well spent. It generates the cost per ton of foregone emissions is much lower than the social cost of carbon. Here is what's called a McKinsey curve, and it shows the marginal cost per metric ton of foregone emissions as a function of the amount of foregone emissions achieved. And so basically the heights of these lines are the numbers in the previous table, and the lengths are how many planes we're talking about, how many planes are going to get scrapped instead of being resold. And so the marginal cost goes up, as you can see. But this marginal cost line is, maxes out at around 20. And so the social cost of carbon is way off the screen, up at 50 or 200 or wherever you want to put it. So anyway, this is a curve that environmental economists like to look at when they're considering pollution abatement. Okay, so the conclusion here is that airlines can be induced to scrap rather than sell their retiring planes at a cost that is worth incurring. If we go and compute the aggregate cost per ton of foregone emissions, basically averaging the numbers that I showed you before, it's $7.64. And that's well below the recent estimates of the social cost of carbon. And so again, to repeat what I said earlier, how this would work is the government would ask the airlines to reveal the identities of the planes set for retirement without revealing their scrap sell plans. And then the government would use its version of our Logit model, and it would offer clunkers payments for the scrappage of planes likely to be sold, assuming that the cost is favorable relative to the social cost of carbon, which it will be. Now, there's a downside to this whole thing in the sense that there'll be fewer used planes around, right? Because the used planes that are being sold are going to be in the garbage heap. And that means higher prices. And that will harm startups and developing country airlines that buy used planes. Those airlines are going to have to buy new planes or use planes that are newer than the ones they were going to buy. And so that's bad news. Maybe what it would do is it would hurt aviation in the developing world. But this is environmentally efficient. It's efficient to do this. If you want to fix the affordability problem for these airlines, the governments in those countries could subsidize purchase of planes. Or something else to offset the affordability problem. Now, there's another issue in that to make this thing work properly, you'd really have to have it done by airlines everywhere. If the U.S. instituted a clunkers program and Europe didn't, well, the developing country airlines could just go and buy their clunker airplanes from the Europeans when they're being retired there. So to really choke off the existence of these old planes and stop them flying around the world, ideally you want to have this program operate everywhere. So anyway, we hope that this idea maybe gets into the hands of policymakers, because this kind of program is quite feasible, can be implemented easily, and it would help. It would help decarbonize the aviation industry. Thank you.
Thank you, Jan. Before I open to the audience, let me just quickly read out a question from Kara. She's comparing your marginal abatement cost through scrapping planes to some work that's been done on the Cash-for-clunkers during the Great Recession, as you mentioned. Yeah, so any
okay, well,
is that something you comment in your paper?
The cost per ton of foregone emissions from the auto program was much higher than ours, and in fact was higher than the social cost of carbon at the time. We quote one of the studies from the 2000s on the auto Cash-for-clunkers, and the cost was at least $90 per ton, and often much higher depending on assumptions. So this is a much more cost-effective way of reducing emissions.
Right, and then Kara's also mentioning maybe that's not something you've done, but to the extent that use steel, right? You can recycle it and you're not using new steel, right? Maybe
Right.
there are other foregone emissions
Right, but
from using that
then
steel sooner.
there's another offsetting thing, which is that with fewer used planes around, production of new planes would have to increase. We don't count the carbon contributions of that production process.
In the interest of time, let me open up to the audience if there is any question.
Well, Jan, I know Alberto and I have talked about this before, but my colleague who's an aerospace expert and chairs like the Cayman Islands Airline Board or something, said that these aircraft don't get reconfigured internally until a major renovation, which is scheduled every 8 years or something. Is that right?
I don't know exactly, but they can increase the seat capacity of the planes and everything, and that's obviously beneficial.
Yeah. Well, anyhow, if you're talking to these airlines, it'd be great to learn like how quickly and expeditiously that could be done. I was thinking having chairs that might rotate or lie down, things that would be more easily movable, so you don't have to wait 8 years, and maybe even between flights, there would be some reorientation of that space as it becomes a long distance flight versus a short distance where people really want more reclining. Things like that would be kind of interesting in case you're talking to some colleagues there.
I also think that there's no data that I know of on this, but that with all the economy plus seating and stuff and the focus on high-end passengers, I think that the seat capacity of planes has gone down. Maybe not for the major carriers. Anyway, not good.
I think that's a great segue to the next talk. But before that, let me very quickly mention that, and I think Matt Kahn, your co-author, like knowing him, I think he would be, interested in something I mentioned in the chat box, that as an alternative to the government providing subsidies, right? Maybe some other agent could provide a platform where flyers who are concerned and they are cutting their flying, but some of the travel needs to continue. They could contribute maybe through Atmosphere. That's a platform I know Cara uses a lot, to this carbon asset, right? And it would have to be, anyway, there's a whole and growing set of regulations in terms of what would qualify as a quality asset, right? But that would be something that, if I knew that this would contribute to retiring one of the old aircraft flown by American Airlines, I would be willing to do that.
Right, but then the thing is that you and I are both economists, and so we know that you need incentives, right? Altruism is not the way to fix this problem. You need to put money on the table, basically, or you need to impose a carbon tax on aviation, which would greatly increase the ticket price, and people would make their own decisions then, and we'd get better outcomes.
Okay, very good. So I am the last speaker. I know we are a little over time, so I'll try and end by before 2 p.m. I always get it wrong, by 1 p.m. Central CDT. So why don't I share my screen? Right, very good. So I think you can see my screen. This is joint work with you'll find Cara's name here, and other amazing mostly economists. Cara is an engineer and also 2 practitioners, and something I'm very excited about. And without further ado, let me get into my slides. So the term cabin cash outs is inspired by a literature that Susan Handy in her keynote earlier this morning talked about, by one of the pioneers talking about parking cash outs was Shoup. This idea that employers provide fringe benefits to employees, and for a proportion of these gifts, the employees that receive these gifts don't value them at the market price. So there's an opportunity for a cash out scheme. But let me step back and talk a little. So this is low-hanging fruit potentially in corporate air travel that's waiting to be picked. Low-hanging fruit both for private benefits, but also social benefits, the reasons we've talked about earlier in this session. So specifically, it relates to the choice or the lack of choice between cabin in business versus economy cabin for high-skilled workers is a fringe benefit, also known as a compensating wage differential. And these workers, they've worked extremely hard in their careers to be in a position to have a business class travel gift from their employers. But now that they've earned this gift, they pay nothing on the margin for traveling in the business cabin. And so the nature of this misallocation it arises from the finding, and we report this finding, that for some of these flying occasions, these workers, they don't value flying in the business cabin relative to economy at the market price differential. So that's what this paper is about. It does matter for the employer, even if the employer were to pass on all of the savings from some of these high-skilled workers cashing out of the business cabin and going economy class, at least for a portion of their travel. Say they're flying back home and they can have the weekend ahead of them to recover. And for the flight back home, they choose economy. So even if the employer were to pass on all the savings from purchasing economy for part of the trip, the employer still stands to benefit through reduced Scope 3 emissions. I won't define Scope 3 emissions here in the interest of time, but this is something that employers are increasingly worried about, and at some point they might have to pay something for these Scope 3 emissions. And I already mentioned that there's this parallel in ground travel, for example, through employer-provided parking, and how much this fringe benefit induces an increase in car travel to work or solo car travel to work. And what I mean by how much, in this literature, you find double-digit percentage changes when you provide better incentives in terms of car travel choices. So there's a very strong parallel to this literature. There's a parallel in terms of income tax distortions. I'll talk a little about that. Similar in terms of employers who provide free cars, free fuel to their employees without giving these employees the ability to cash out, which would introduce an opportunity cost. So these are all terms that I'll cover in my short talk today. So it's about corporate travel policy today, the established corporate travel policy for the high-skilled end of the workforce. So I'm thinking about managers, consultants, so managers from middle managers and above, consultants, scientists, even policymakers. These are jobs, some of these require long-distance travel. So going back to Dr. Wadud, who talked about long-distance travel, they typically have a gift. It's a fringe benefit. Whenever they travel, the employer gives them a ticket, which is a business class ticket. And so the employee's choice set is they either fly in the business cabin or they insist to go in the economy class cabin, but they both face zero price. There's a zero price on the margin. So, this is a picture from on the brand ambassador for Emirates, this Hollywood actress, Penelope Cruz, and there's the glamour, and, to the extent that she's an employee of a firm, she's paying nothing for being there. She's not at least giving up any real money for being there. So the idea of our project is for the employer, through either regulation or voluntarily, to create a secondary market that is inexistent. So what do I mean by this? That today, if a worker, let's say not a high-skilled worker, low-skilled worker, has an economy class ticket, the airline allows the employee, even at the check-in, to upgrade to business class. So that's a secondary market that does exist. But on the other hand, the high-skilled worker who has a business class ticket cannot trade down to economy class at the check-in, say, listen, I'd like to cash out, and instead of flying business class, I'd like to receive a few $1,000s on this flight to cash out. So that's a secondary market that doesn't exist. And so what our project is about is in terms of the employer creating this market. So here's an example, London Heathrow to Singapore. Let's think about one way to fix ideas. These are kind of real numbers. This is just for a one-way flight. a long distance one-way flight, nonstop. If you fly in the business cabin, you might pay $4,000 from to British Airways or Singapore Airlines as a duopoly for nonstop. The skies, as we know, are not open; they're closed. Or if you go in the economy cabin, you pay $1,000. Today, the established practice is let's say the director of a firm would receive a ticket for business class. But what we would propose is instead of a ticket, the director receives an allowance, a $4,000 allowance for that flight. And now the choice set for the employee is either to stay on business class and consume all that allowance, $4,000, or to cash out, go economy class, say that's ahead of the weekend, going back home, or take a day flight, and receive a $3,000 cash residual. So that's this idea that we're talking about. Okay, and so here's again Penelope Cruz. She's an employee, and she's decided to stay in business class. And what we'll document today is, most high-skilled workers would stay in business class, but around a third would cash out. So she's decided to stay in business class, but now she is paying a price. Not that she's paying it out of pocket, but she has given up real money, $3,000, to stay in business class. So she's thinking maybe the next flight I could consider going in economy class and keeping $3,000. It's a triple win. The employee definitely enjoys more choice. So this is an important travel input to component of the person's work performance. Most workers might not care, but to those who do care, it reduces their personal carbon account. For the employer might save some money if the employer doesn't pass on the $3,000 in the example, but the employer would also report lower Scope 3 emissions. And it is good PR. It's not a greenwash, it's a good PR. And environment, as we'll talk about later, it would have an impact on raising passenger load or the number of passengers on a plane, the occupancy. In the long run, once airlines adjust fares, adjust cabin configurations, there would be a reduction in the number of planes and a reduction in climate damage. And so I'll come back to these as I go along. Okay, so a bit more on why this matters in 2024. I think I'll go very quickly through that. We've had comments by Dr. Skowron on that, the rest of the talk. Then I'll very quickly give you a glimpse of an oligopoly model of vertical product differentiation that we have in the paper. I will, save you from algebra and so on. I do want to spend a moment on an intercept survey that we did at a major airport of managers flying in business class. So this is a proof of concept where we sought to elicit the reservation value for flying in business class. And then I'll spend a moment on another part of the empirical aspect of the paper, which are these focus discussions that we did with senior managers, academics, and policymakers to understand the frictions, the feasibility and acceptance by employers and employees of a transition to, instead of employers giving employees tickets, employers giving employees allowances and letting them choose, giving them more agency over their travel inputs. So in terms of what we find, I'll be running out of time, is in our oligopoly model, once we give employees an allowance, so what this means is high-skilled workers would get an allowance equal to the business class fare. What we see is around a third would cash out into economy class. This reduces the demand for business class, so there's going to be a price response. So airlines will respond, reduce business fares, raise economy fares. And so that does undo some of the decreased business cabin demand. It doesn't undo it entirely. The other finding from the intercept survey is, as I mentioned, around 1/3 of flights on business class by high-skilled workers would cash out to economy class. So that's, again, in the order of magnitude of the parking cash out literature. And for employers, this would entail a 7 to 9% reduction in Scope 3 emissions from air travel. So that's a pretty sizable shift. And in terms of our focus discussions with senior managers, what we heard from these different managers who have experience either in traveling in business class or setting policy is that there are some principal agent concerns, like, for example, a manager who now cashes out into economy class because they're cheap, quote unquote. They might, arrive less rested to a meeting, and that could have a productivity loss that the employee might not internalize. So these are some of the thoughts that surfaced and help us understand what the obstacles could be to widespread adoption. Okay, I have a slide here on the science of climate damage from aviation. Dr. Skowron did a great job. This is actually the same, in the middle, the same graphical abstract that she showed us in one of her slides, so I'll just skip that. I think this has come out as well with Dr. Wadud. The aviation sector is hard to abate. It's known as a hard to abate sector compared to, for example, decarbonizing road transport, electricity generation. Highly popular. The elasticity of demand, income elasticity of demand for air travel is higher than 1. We saw that trend. Dr. Wadud showed us the trend going up in the UK. I do want to emphasize that aviation is a highly valuable sector. It's not only about costs. It's a key input to economic development. Some papers in economic literature on that. But importantly, the backdrop to all this is that the circulating fleet is set to triple by 2050. So whenever we think about reducing emissions, what we really have in mind here is reducing the increase in emissions. Okay, so it's not that they will likely go down. For the individual, there's a slide in Dr. Wadud's presentation that looked at this, and some in the chat box. For those of us who fly, and we think about our impact in terms of the carbon emissions or the greenhouse gas emissions or the climate damage embedded in our consumption, air travel dwarfs other domains of consumption. So, it's not a number that is easy to obtain, but for those of us who want to work through these calculators, it's it's the dominating component. And that even if you just travel economy class, let alone business class. Another thing that's come up in the conversations is, highly unequal. This is a Lorentz curve coming from a nice paper by Oswald et al. If you think of the share, the 10%, you can see my mouse here, the 10% share of the population with most travel, they account for maybe 90% of the climate damage from emissions. Here, I think it's just energy, but it's a similar idea. So it's highly unequal. There's the ethical aspect also mentioned by Dr. Wadud and others, and Dr. Skowron. Okay, so very quickly, the oligopoly model of vertical product differentiation. This is long distance air travel, seats in business and economy cabins. They're vertically differentiated substitutes. What does this mean? That at equal prices, we all agree that business class is the better product. In the model, we have work travelers of 2 types, high skill. These have a business class privilege, and low skill. Low skill doesn't mean low skill, it means just lower skill. So maybe someone who just travels for work, but has a economy ticket. These work trips, they create enterprise value. And whenever the work trip is higher than the cost of travel, they're authorized. And to emphasize pre-policy change, the widespread scheme is the worker gets a ticket from the employer. Okay, so if you're a high-skilled worker, you get a business ticket. If you're a low-skilled worker, lower-skilled worker, you get an economy class ticket. In the model, we've also got leisure travelers. Some of these are workers, so that workers double as consumers going on vacation. We've also got retirees, right? So no longer workers. We have a high income and low income leisure travelers that will shift their price sensitivity of demand. So low income workers, they value dollars more relative to the quality of the transit on the aircraft relative to the high income. These leisure travelers know there's going to be some value to leisure trips, only leisure trips that exceed a certain threshold given by the price of travel will happen. So all of this is in the model. I know I'm running out of time, so I will go very quickly through this. We first consider a monopoly airline. So think of this as one airline servicing the Singapore-London route nonstop. And then we have another section of the paper where we relax this and consider a duopoly. So the example of Singapore Airlines and British Airways. Right, so I don't think I have much time to talk about this, but I'll stay on the headlines of these slides. So work trips create value. This is this box over here. Whenever the value of a trip, the enterprise value of a trip, kappa exceeds, like if you're a high skilled worker, exceeds the cost of the trip, the airfare, then these trips happen. There's a distribution of preferences over a business class and economy class. So for example, say that I'm a worker and my preference is, this is on this top left panel, this is the value for the transit in economy class to my destination. I'm on the vertical axis, the value to being in business class. Say that I'm over here. This is the diagonal. So what this means is I do value business class over more than economy, but by this amount. In the pre-policy, everybody who has a business class privilege flies in business class because they just get the ticket and you cannot downgrade. For low skilled workers, I would be, for example, over here. This is my preference, and I do not value business class relative to economy class at more than the airfare difference adjusted by my price sensitivity demand. So I would stay in economy class. Maybe there are a few there's some low skilled workers who really value being in business class, and they might upgrade on their own account, on their expense. And so in the pre-policy, we have high skilled workers flying business class, depending on the distribution of preferences. We have low skilled workers traveling economy class. And what the change in policy does is it shifts the high skilled workers' incentives to the right top panel. So if I were, for example, a high skilled manager, and I received a business class allowance, and so I'm in my example, I'm over here, I do not value business class relative to economy class in excess of the price difference. So I would take that allowance, I would go economy class, and I would cash out on the $3,000 difference, okay, just by this change in policy. Okay, I'm running out of time, so I'll just skip the leisure travel. The model is very straightforward to solve. We do this numerically. Given a policy and fares, we can solve for demand by workers, high skill, low skill, demand for leisure travelers, high skill, low skill. So in this example is the demand for business class. Over a 5-year horizon, something I did not mention, but a business seat, there's a literature on this. It occupies a space about 3 times the space of an economy seat. And so you can calculate based on the demand over a long-term horizon, airlines are meeting demand by configuring cabins. And so X here is the space on the aircraft that's allocated to the business cabin. You can include the profit function for the airline. There's going to be, the airfares, PE and PB. There's going to be demand, and then there's the marginal cost. So the marginal cost, you could think of airlines leasing planes, and so that makes it a marginal cost. I'm running out of time here. Let me just skip the monopoly simulation and go straight to the duopoly simulation. So the first column is the existing travel policy. So what it shows us is the economy fare is set at marginal cost. You can think of this as a homogeneous product. And the business fare would be $3,600. And these are the duopoly airlines are maximizing profit given what the other airline is doing. For high skilled workers, so 30% of these occasions don't involve trips, but for those that do involve trips, adding enterprise value, all these workers are going in business class. You can look at the shares for low skilled workers, high income vacationers, low income vacationers, calculate the percentage of passengers in business class. In this example, it's 14%. It's around the same value as what's reported in the literature. You can calculate the misallocation of business seats, which is people who are traveling in business class, high skilled workers, who would rather cash out if they had the option. And you can calculate the scope 3 emissions. The next 2 columns, the first column considers the short run where maybe a few employers, they change the travel policy and set allowances. So high skilled workers get an allowance equal to the business fare, low-skilled workers get an allowance at the economy fare. And so you don't get an adjustment in fares or in cabins. And so you can calculate the reduction in Scope 3 emissions. So in this case, it's around 8%. The rightmost column is, you think about the long run, say 5 years, 5 to 8 years, as Kara was mentioning, and you allow, you assume that there's a widespread adoption of allowances by employers, and then there's a change in airfares and a change in cabin configuration. So in this example, the widespread adoption of allowances by employers would induce a 2% reduction in the price of the business, in the business fare. So you have to allow for that. And the reduction in Scope 3 emissions, it would be a little lower. So instead of 8%, around 7%. Okay. Spend a few moments. I've pretty much run out of time, but we did a proof of concept out of Changi Airport. We did 2-minute intercept surveys at the Singapore Airlines terminal. This is not an easy demographic to access. They have very high value of time. So we had to think of eliciting willingness to pay in a very direct fashion. What we did is we would observe passengers checking in the business class counter. And as they were walking over to passport control, we would ask them if we could have a few minutes of their time to understand their travel preferences. So we approached 370 passengers. Some of them didn't qualify because they were maybe checking in at business class counter, but they're actually leisure travelers, so they don't have employers funding their travel. They could be applying so we had to screen out some passengers. Some didn't want to participate. In the end, we had 150 participants. We had a first question, which was a warm-up question, where we asked passengers that would be willing to cash out of business class to economy class for this trip. Obviously, they've already checked in. It's a warm-up question. 80% said, no, I wanted to stay where I am. I don't want to cash out. But that was really a warm-up question to the second most important question. I'll get this in a moment. But in terms of passenger characteristics, we had a good mix of medium haul passengers, long haul distant passengers, ultra long haul. Most, our median passenger, if you will, is middle-aged, is male. The top destinations were Hong Kong, London, New York, Sydney, and Frankfurt. So it was a good mix of travel. The second question was the most important, which is where we asked travelers for their next trip to that same destination. I don't have time to go through the wording, but we did the basic idea of what we did is we wanted passengers to tell us at what value, if they receive cash in their next trip, at what value would they downgrade to economy class? And so this is a demand curve. There are some passengers that are high willingness to pay or willingness to accept to downgrade to economy class. Some are less willing, they'll stay in business class no matter what reward they receive. These different panels are by the distance. So we elicited these demand curves. We then pair demand with supply. So we assume that the employer would pass on 100% of the savings. There's some algebra here. You can calculate the cash out share. And let me summarize here. At the existing fares, around between 14 and 32% would cash out of the business cabin. So it points to this deadweight loss of gift giving in terms of air travel incentives. There's a seat misallocation that we can quantify. We can quantify the Scope 3 emissions. We do a back of the envelope calculation, thinking of the long run. If employers, the widespread shift was, if you do offer business class to your executives, you have to offer the option to downgrade. You're creating the secondary market. This could come through regulation. We calculate the shift in emissions. I will get to that in my summary slide. We had a question on social norms. We provided the carbon emissions, the carbon equivalent emissions for travel. What we see is the demand to downgrade does shift out as this blue curve to the green curve. Part of it is an experimenter effect because we're telling the passenger what the climate damage from the travel is. So it's there's some of this is a bias. It's not a big part of our paper. This we did only at the end. I will skip all this. The focus discussions with policymakers, I mentioned this at the beginning. There's some concern about productivity loss and that the employer, the principal, cannot let the agent decide and has to decide on behalf of the agent. At the same time, everybody agrees that these are, highly motivated, highly skilled individuals. They have skin in the game. If there is a productivity loss from cashing out to economy class, they'll probably compensate through other inputs. And so giving workers more agency over travel inputs, just like they can choose typically the airline, the time of the flight, also letting them choose the cabin of travel rather than the employer deciding on behalf of the employer, that could be justifiable. Okay, then I will, there's an example of how NUS might be going down this route where instead of giving visitors a ticket, the idea of giving visitors an allowance, letting them choose and maybe doing some carbon labeling. Although, climate doesn't sell, so you've got to be always very careful how much you try to sell because of climate. The takeaways is cabin cash outs. We provided proof of concept of low-hanging fruit in corporate travel. This could be implemented through fixed allowances. This would involve a triple win. Around, let's say, 15 to 30% of flights could involve voluntary downgrades. For the employee, it's more choice. For the employer, it's lower Scope 3 emissions. For the environment, it's in the long run, higher occupancy per flight, something like 3 passengers per flight, from shrinking the business cabin a little relative to what it will look like. There's a huge opportunity for a willing employer to do a pilot over a limited campaign, maybe to test whether there would be implementation frictions like principal agent frictions. And the last bullet point, if this were to be scaled up, we could reduce seat misallocation in the order of tens of billions of US dollars per year, and we could reduce Scope 3 emissions by employers by tens of millions of tons of CO2 equivalent each year. And on that, I'll stop. And I know we're over time. So maybe if there's any pressing question, maybe we just move on to the next session.
Thanks so much, Alberto. He's the moderator, but hey, I've been creating this BTR series for 6 years now. And those of you who are in different disciplines like aeronautics, I'm not sure, Agnieszka, what you're in. And I think we had a mechanical engineer, maybe no, that was in another session for me, but econ, obviously, we should be having these kinds of meetings in every discipline. So anyhow, they keep showing the slides here. This looks great. I think it's Hannah. I forget the name of our tech staff, or Sagan. Thank you so much. He's our main host. But yeah, you've got 3 other sessions you can shift to. I think you know how to reach Alberto and me. So any questions you have, Zia's going to get back to me on a couple of things, and Agnieszka has already sent me her paper and or her slides. So I will hope to share that with about 3,000 people on our listserv, because that's why we organize a BTR. That's a big reason why we do BTR.